I'm Charles Cooke, the Sustainable Energy Technology Lead at TTP, and today I'm going to be talking about the challenge of more. And in this context, the challenge of more means the challenge of meeting the targets that have been set for installed capacity of electrolyzers for producing green hydrogen. So the structure of my talk looks like this. First of all, we'll have a brief look at how much more and the targets that have been set, and then to add some colour to the numbers, see how that measures up in terms of everyday things that we're all familiar with. Then the main part of the talk, which is about what is the role of technology and system development in enabling the scale up of the installed capacity of green hydrogen electrolyzers. And then finally, the call to action, which is about forming partnerships for success. So firstly, the targets in terms of numbers for how much more, what are the targets that have been set? And here I'm referencing with thanks the International Energy Agency, who have published several really interesting reports, two of them listed there at the bottom of the page. And according to those reports, and this is a rapidly moving situation, so the numbers here are kind of a snapshot in time, but I think however much they've moved slightly since then, since 2021 when all of these reports were published, some of them I think, it's the kind of orders of magnitude still hold and the message is still the same. So if we take as the current figure 30,000 tonnes per year of green hydrogen that can be produced using the entire installed capacity of green hydrogen electrolyzers now. That's the current figure, 30,000 tonnes, and that's equivalent of about 250 megawatts of capacity. And the projected need by 2030, which is less than a decade away, is 850 gigawatts. So 850 gigawatts compared to 250 megawatts, that is an increase by a factor of more than 3,000 times. So that is a staggering step up that is required. So their numbers. What if we actually think about these things in terms of everyday objects and things that we can imagine and relate to? The process of producing green hydrogen is splitting water. So if you imagine an Olympic swimming pool full of water, the current global installed capacity of green hydrogen electrolyzers would take around about 3 days to split a swimming pool full of water. But by 2030, the target is that a swimming pool full of water could be split in around 12 minutes. So 3 days to 12 minutes is a big change. Then if we look at the actual electrolyzer itself, at the heart of a green hydrogen electrolyzer are cells, and these are generally arranged in stacks, so a stack of cells. And for membrane technologies, at least, there's a membrane that covers the area of the cell. And if you took, if all the current green hydrogen electrolyzers were membrane based, which they're not, but for the purpose of this illustration, let's just assume they are, you take all the membrane out of all the electrolyzers and lay it out on the ground, you'd get 3 football pitch areas of membrane. So by 2030, that needs to increase to being able to completely carpet the City of London 20 times over. So massive increase there. And if we look at the actual amount of hydrogen being produced, currently all the green hydrogen produced in the world, if you put it into a lorry, you'd fill a lorry about every 10 minutes. So if you're standing on a road and all the world's green hydrogen was being lorried past you, one lorry would pass every 10 minutes, which probably wouldn't keep you awake at night. By 2030, 5 lorries would be filled every second. So you'd need about a 15-lane highway just for all the lorries to go past without getting any congestion. And currently the power for the world's green hydrogen electrolyzers could be provided by around 50 wind turbines, but by 2030, if targets are met, 17,000 wind turbines will be needed. So that is kind of an illustration of the scale of the challenge, how much more green hydrogen electrolyser capacity needs to be installed and commissioned. So looking at this from another axis, which is the financial axis, 850 gigawatts of electrolysers, how much is that worth? So if you assume $200 per megawatt, which is a very ambitious target, that still gives you, even with that ambitious target, still gives you $170 billion worth of electrolyser equipment to install. And the $8.5 billion is just the value of new systems that would need to be installed at that point to maintain the capacity, if you assume that the lifetime of each electrolyser is around about 20 years. So we're talking large amounts of money that need to go in. So a big business, so plenty of space for lots of players to work together. So what part can technology and system development play in enabling growth? So that's the big question at the centre of this talk. So I've been to a few expos and events around green hydrogen in the past few months, and there are some themes that are coming out and are common to all of them attending the presentations. So this diagram summarises 4 key ingredients that there seems to be general consensus are required for green hydrogen growth. They are bankability, so people financing new systems need to have confidence that those systems are going to work and that there's a market for what they produce. Availability of systems, the total cost of ownership to make the hydrogen that the systems produce affordable, and the cost of electricity, of renewable electricity, has to be at a level that again makes the hydrogen affordable. So technology and system development play a part in at least 2 of those 4 ingredients. Firstly, availability. The design of the system is critical to making it manufacturable, and the technology inside. And then also the technology inside and the engineering of the system is critical to the total cost of ownership. It affects the capital cost, the cost of building the system, the operating efficiency, so the cost of actually powering it, and the cost per kilogram of hydrogen produced. It affects how long the system lasts and how often it needs to be serviced and how much it costs to service, and it affects the cost of decommissioning and recycling. So technology and system development are at the heart of all of those issues, which are critical to the viability. So before we get into the detail of where technology plays a part in these systems, it's helpful to kind of take a big step back and look at what the systems actually do. So on this slide, there are 2 water molecules shown, the big red red oxygen atom with the 2 hydrogen atoms on top. And so the electrolyser takes those water molecules and splits them into hydrogen ions and oxygen ions, and then those ions are separated and recombined to make hydrogen gas and oxygen gas. So in principle, very simple, and the challenge, the engineering challenge and the technology challenge, is to create the conditions for this to be done abundantly and at a commercial cost. Of course, when you actually get to designing a real system, it gets rather more complicated. So here's a picture of a small lab scale cell, and you can imagine here, you can use it to imagine the various challenges. So you have to feed water to the reaction site to keep the reaction site fed, and then you have to transport the gases away from the reaction site once they've been produced. You have to transport electrons to and from the reaction site at either side, and because the system is not 100% efficient, you have to deal with the excess heat. And then around the whole plant, you have to make the water pure, and then you have to condition the hydrogen and get it into a format that it can be taken away and used profitably. So it's a complicated process, and clearly technology has a big part to play in making that optimized. And we TTP are very much involved in at this sort of fundamental level of optimization. And this illustrates our kind of dual approach of using modeling and lab experimentation hand in hand to guide each other. And the videos here, the movies that are playing in the model, are showing the predicted changing concentration in various species in response to cyclic variation in the electrical conditions. So this is a phenomenon that's exploited in electrical impedance spectroscopy, which is a way of figuring out what's happening inside the cell just by using parameters that you can easily vary outside the cell. So once you've designed and optimized the actual cell, to make the electrolyzer feasible and viable to be rolled out rapidly and to make an impact on the world, it has to be manufacturable. And to be manufacturable, it is massively advantageous if the system manufacturing process can use equipment and processes that are well proven and mature in other industries. So in other words, if we can sort of stand on the back of things that are already in place. Now there are various sort of levers that we can use as engineers and technologists to make our solution fit existing processes. And one of those levers is by adjusting the scale of the various modules inside the system. So for example, the amount of the capacity of an electrolyzer comes down to the area, the combined area of all the cells in the system. So you can have a single cell that measures 10 meters by 10 meters, or you can have a million cells that measure 1 centimeter by 1 centimeter. So they both give you a megawatt's worth of hydrogen generation capacity, and you can have anything in between. And the key to success is scaling things so that they fit existing processes. But to be able to do that, you need to know what existing processes exist in different industries. And that's where the partnership thing comes in, because if we're partnering across disciplines and across different market sectors, then we have access to technologies that are used in different market areas. And this is something where TTP has a big advantage, because we work across lots of different market sectors, and we're able to draw on technologies that are common and established in adjacent markets. So a lot of focus when people are thinking about green hydrogen electrolyzers is on the cells and the stack, and that's where a lot of the IP is. But if you look at where the value is in a green hydrogen electrolyzer, a lot of the value is in the balance of plant. So that's all the systems around the stack of cells that are required to make the stack function properly. So they include the systems that purify the water and get it ready, the systems for circulating the water, pumps, heat exchangers for dissipating excess heat, compressors and gas purifiers. So all of these systems, and many of these are mature and used in other sectors. So they're often supplied by companies that have a long history in manufacturing them. So for these companies, there is a massive opportunity with green hydrogen to which is effectively a new market for their existing products, or products that are close to their existing products. But a challenge for these companies is in figuring out what the requirements are and how they need to adapt and reposition their existing portfolio of products to make them suitable for the green hydrogen market. And this is something where TTP is an independent technology company with domain expertise, can provide advice, and not only provide advice, we can help to adapt an existing portfolio of products to make it optimized for the green hydrogen market. Reliability is key to any plant that's going to be operated successfully, and this is key to that ingredient that I talked about earlier, which is the bankability. If a finance provider is going to help to finance a system, they need to know that it's going to last and it's going to deliver as it should do for the whole of its projected life. So reliability engineering is something that is very key to what we do at TTP in helping our clients commercialize their products. And the dendrogram on the left is a nice visual way of showing how the reliability of all the different components contributes to the reliability of the whole system, and it's a nice visual way of mapping that out. There are also other complexities in reliability, of course, to do with the interaction between adjacent systems, particularly with an electrolyzer where you have the complex balance of plant and many subsystems. So one subsystem might operate with sufficient stability for it itself to be reliable, but it might be creating instabilities that for neighbouring systems are causing them to operate outside of their sweet spot and making them less reliable. So investigating and understanding things at a system level to be able to spot these interactions is an expertise that we have, and often when the difficulty is in actually identifying these kind of weaknesses, the solution can actually often be quite simple. So that's reliability. Another aspect of reliability is sensing, of course, and monitoring the system. And sensing is something where we are an area where we're very active at TTP, and we have several sensing technologies where we have IP, and one of these is a low-cost hydrogen sensor that it has a very long life, that works on a speed of sound principle called sonic sense. So now for the call to action and the partnerships for success. So the two themes that have run throughout this talk are partnerships, bringing people together and working across different market sectors. So bringing in balance of plant providers who are more commonly associated with other industries, and working together to make this target a reality. So that's the partnership aspect. And the other aspect is technology. So using technology to optimize the system at its core, and using technology to make the system manufacturable and to make it ideally manufacturable using established equipment and processes that can rapidly be ramped up again to help meet the targets for scale. So technology and partnership, and we are the technology partnership TTP. So you can see where this is going. So really encourage everybody listening to this talk to get in touch and start a conversation and to explore possibilities for new partnerships to accelerate the growth of sustainable energy provision. Thank you very much.